Yes. Yes. On your blue packet, we are approximately on page 3, which is also the second sheet. So if you turn, it's the second one. We're right there at the top. Smack dab right up there at the tip. Awesome. All right. So yesterday we learned about a complex number. We said that this was the standard form of a complex number. Okay. It's got its real part A. It's got its imaginary part B. Okay. Together, it makes a complex number. Okay. We're going to figure out 2 other forms of complex numbers today. Okay. The first one that we're going to do is relatively familiar for you. Okay. It is the ordered pair form of a complex number. So the ordered pair form is A, comma B. Now, truly, when we're dealing with complex numbers, okay, that imaginary axis is kind of like our 3-dimensional axes. So in a normal Cartesian system, we've got x's here, we've got y's there, and then our imaginary axis would be like our 3rd-dimensional axis, so it would be coming out of the screen or coming up off your desk would be that one. Okay, which is hard to graph. Okay, so what we do then is we kind of break it down and we say that this now is my real axes. So that would be like the A part. Okay, and the vertical or the other one is the imaginary. Okay, and so that then would be the B part, okay, which is why we can do that ordered pair A, comma B, because then that way we can graph it on a 2-dimensional sheet of paper, and we don't have to, go downstairs to the tech ed department and get a 3D printer to print it out and put it in a certain spot.
So do we have to write out which ones are imaginary axis and which are
Yes.
to make sure it's not.
Yep. To make sure, so that you distinguish between X and Y and imaginary and real. Yep, exactly. Okay, all right. And then in about 10 minutes, I said 20 in the first class, but then I looked at the clock and I'm like, oh, it only gave me 10 minutes. In about 10 minutes, we'll find the third form, which because we're in pre-calc and it's all about trig right now, that third form is going to be called the trig form of a complex number. But we'll get there in a minute. Okay? All right? So, let's let Z be 2 minus 5i. Now, that's the standard form, correct? Okay? So, if I were to put this in my ordered pair form, that would be 2, comma, negative 5. Do we all agree with that? That would be the ordered pair form of it. Yes? Okay. So if I want to make a sketch of that, so now this would be my real axes, and this would be my imaginary axes, and we can do R and I there. If you write it out, you write it out. It's all good in said hood. Okay? Doesn't matter to me. Okay? So if I want to plot the point 2 comma negative 5I, well, that means that I'm going to go 2 in the positive direction of my real axes, and I'm going to go 5 in the negative direction of my imaginary axes. So that puts me right there, is the point 2 comma negative 5, or 2 minus 5I. Right? Yeah. So that's graphing. Just like you've been graphing for years in the XY coordinate plane. Okay? We can graph now in the real and imaginary plane. Okay? So let's talk about that specific point, 2 comma negative 5, or the point 2 minus 5I. Each and every complex number is a certain distance from the origin. Wait a second. So what I'm saying there is I'm saying that this, let's get it nice and purty, that this is a certain distance from my origin. Yeah? What do we normally call that? Or what have we been calling it when we were dealing with vectors, when we were dealing with polars? What did we call it? It was like the magnitude in vectors. What do we call it in polars? Radius, or just r, right? Okay. So which one's easier to call it? Radius or magnitude? Radius. So let's just call it r. Yeah. So that's r. So that's r. Makes sense, right? Distance. Yeah. Okay. All right. And it's on a directed ray. Directed ray? What do we call that? Or if we go back to vectors, vectors had a direction, right? Okay. So that was an angle, yeah? In polars, the points all were, we found them with a certain angle, yeah? So what are we going to call our directed ray? Theta. Well, how are we going to find theta? So theta really is right here, right? It's our trig angle. That's pretty cool. Got it yesterday. Why are you yelling at me? Okay. So, the next question then is, how do we find those two? Well, in vectors, let's deal with r first. In vectors, how did we find r? Or in polars, how did we find r? Or in this, how do we find r? Dylan? Okay, but I'm not dealing with x and y now, am I? Okay, so r here is going to be, you just said, the square root of a squared plus b squared, right? Because it used to be x and y when we were back in Cartesians, but now that we're in or complexes, I should say, it's a's and b's, right? Okay, that works. So that gets me r. Okay, really what we're doing is we're making, somebody had said it before, I don't remember who said it over there before, but really what we're doing is we're making that right triangle right there. And doing our right triangle trig, or RTT. Okay, so how would we find theta? Boom goes the dynamite. Okay, so theta really is a reference angle, and that's going to be the inverse tangent of b over a. Now my question is this. Are there any things that I have to deal with in that? Are there any conditions? Drop the negative, so we still have that. And it's only a reference angle, right? So actual theta in quadrant 1, what is actual theta? It's the same as our reference angle, right? Okay. In quadrant number 2, how do I find actual theta? 180 minus our reference angle. In quadrant 3, 180 plus our reference angle. In quadrant 4, 360 minus our reference angle. Okay? Just like we've been doing for a while now, for a couple months. Okay? On Friday, last Friday's quiz, there were still some people that are going off of the vertical axes to find finding reference angles. Not good. Okay? Remember, we always go off the horizontals. Okay? All right? Yeah, sounds good. I like it. So now, let's go back to our z is 2 minus 5i. That one. Okay? How do we find the complex number in trig form? Okay? Well, actually, let's tap the brakes. Let's not go there yet. Let's find it. Let's go down here first. So there's all that. So now, in polar form, or in vector form, we said that x was equal to r cosine of theta. Yes? And we said that y was equal to r sine of theta. Yes? Okay. But we're not in that rectangular Cartesian grid, right? We're in our real and imaginary one. So really, x is what? X is really a. Let me see. Let me go with black. X is really a, and y is really b. So if I say that in an imaginary if I say that z, and we're going to call in our imaginary form, we're going to call all of our numbers z. Why? I don't know, but we'll just do it because it's cool. Okay? We're going to say that those are a plus b times I, right? Well, what's a? R cosine of theta. So that's going to be r cosine of theta, right? Plus, what's b? R sine of theta. And I put that r sine of theta in parentheses because I don't want to get it confused with that. We're taking that imaginary part and we're attaching it to theta and then taking the sine of an imaginary number because that would just be silly. Okay? All right? Mathematically speaking now, can I do anything with that? Can I do anything with this to make it look a little easier? Factor out an r, okay? So let's factor out an r. So then that's going to be z equals r times, what's left over is the cosine of theta, right? Plus, now I'm going to bring the I in front. And so this is the trig form of a complex number. Okay, so that's our third form, our trig form. Okay. Now, let's go to it. Let's do it. Okay? So now we're at 2, comma, -5 in the real and imaginary plane, or 2 minus 5i, and we want to make the trig form. Well, the first thing that we need is we need r. So r is going to be 2 squared plus -5 squared, and I'm going to take the square root of that. Okay? So that's going to be 4 plus 25. Now, another thing that we found on the quiz last week, Friday, was we're having a hard time squaring radicals and squaring negative numbers. Because if I were to type in the calculator, if I were to type in -5 squared, that's going to square 5 and then make it negative, because that's the order of operations. If I wanted to do that, I would have to put parentheses around it. Or my other option is, because you've done it 1,000 times, -5 times -5 is positive 25, because you know that a negative times a negative is a positive. Okay? Well, let's move on from that. I'm over it. So this gives me r is the square root of 29. Do we all agree with that? Okay. Then we have to go on and we have to find theta. So theta prime is going to be the inverse tangent of 5 divided by 2, b over a. Somebody with a calculator, help me out. What is the inverse tangent of 5 over 2? 'Cause really it's like 68.199, right? So 68.2, I would agree with. Okay? Which quadrant is this imaginary, or excuse me, which quadrant is this complex number in? It's in quadrant 4, right? Because 2, -5 was down here, so that tells me that I am in quadrant 4. So when I'm in quadrant 4, my actual theta is equal to what? 360 minus my reference angle, and my reference angle was 68.2. So that tells me that my actual theta is 291.8. Yes? So the trig form of z is the square root of 29 times the cosine of 291.80 degrees plus I times the sine of 291.80 degrees. Yes? Yes. Okay. Questions? So we now have three ways to represent a complex number. We have our standard form, we have our ordered pair form, and we have our trig form. Okay. And we can switch forms. The first two we can switch relatively easily, right? But we got to do some extra figuring in order to get into that one. Because coming along with this then is our r equals the square root of a squared plus b squared, and theta prime is the inverse tangent of b over a. So let's put that to work now. So we've got z equals negative 3 plus 4i. If that is which form? That's standard form. Let's put it in ordered pair form. What would my ordered pair form of that be? Negative 3 comma 4. Fantastic. So there's my ordered pair form of it. Now let's put it in trig form. So the first thing that we need to do is we should find r. So r is going to be negative 3 quantity squared plus 4 quantity squared, and take the square root of that. Well, that's 9 plus 16. 9 plus 16 is the square root of 25. So r here is 5. Do we all agree with r being 5? Yes. Okay. Then we need to find theta. Okay. So my theta prime then is going to be the inverse tangent of 4/3. What is the inverse tangent of 4/3? 53.13? Yes? Okay. Which quadrant is this complex number in? It's in quadrant number 2. Okay. So because it's in quadrant 2, what do I do in order to find my actual theta? 180 minus 53.13. So that's going to give me my actual theta is what? 126.87 degrees. Okay? So my reference, or not my reference, excuse me, my trig form, z, is going to equal 5 times the cosine of 126.87 degrees plus I times the sine of 126.87 degrees. Yes? Okay. What I would like you to do now is I would like you to find numbers 2, 3, and 4. Okay? And then in a couple of minutes we'll go through, I'll start doing those. Okay? If you're listening online in Mrs. Hill's afternoon class, now you could pause, do numbers 2, 3, and 4 in your packet, and then restart. Spot checking number 2. So the ordered pair form of this complex number is negative 2 comma negative 2 square roots of 3. Okay, we just basically get rid of the I there in on that second one on that B. So I need to square negative 2, and I need to square negative 2 square roots of 3. So I get 4 when I square negative 2. I get 12 when I square negative 2 square roots of 3. Because it's negative 2 times negative 2 times the square root of 3 times the square root of 3. So that's 12. 4 plus 12 is 16. And the square root of 16 is 4. Okay? Then I need to find the inverse tangent of my angle. So that's going to be b over, or I need to find the inverse tangent of this point. So that would be b, 2 square roots of 3 over 2. I drop the negative signs. So really that's the inverse tangent of the square root of 3. Okay? And that is on my unit circle. That is 60 degrees or pi over 3 radians there. Because I am in quadrant number 3, I'm going to take 180 and I'm going to add my reference angle to it. So my theta is really 240 degrees. So my vector z is 4 times the cosine of 240 degrees plus I times the sine of 240 degrees is my vector there. Yes? Fantastic. For number 3, because it's 0 plus, or it's just 8i is my complex number, that really is 0 plus 8i, which in ordered pair form is the point 0, 8, which is straight up 8 from the origin in my real and imaginary axes. So the distance that I am from the origin is 8. And my theta, straight up, is 90 degrees. So my complex trig form is z equals 8 times the quantity of the cosine of 90 degrees plus I times the sine of 90 degrees. In number 4, I get r is equal to 10, and I get my reference angle is 30 degrees. And because I am still in quadrant number 3, my reference angle, or my theta, I should say, is equal to 180 plus 30. So theta here is 210 degrees. So my vector, or I should say vector, my trig form of my complex number is 10 times the quantity, the cosine of 210 degrees, plus I times the sine of 210 degrees. Okay? Have a good day.